synthesis. Let's say you want 1,2 dinitrobenzene. In practice, you never start with benzene. One, because it's a carcinogen, and two, because you can buy just about every substitution on benzene that you can imagine, because the chemical companies are doing all kinds of different reactions. But as a thought exercise, how would we convert benzene into 1,2 dinitrobenzene? And the crux of the problem is that NO2 is a meta-director. So if you just take benzene and react it with HNO3 and H2SO4, you can certainly make nitrobenzene. But then if you keep going, maybe use 100% nitric acid because the nitro group has just deactivated it. You can put multiple nitro groups on. But the product would be 1,3,5 trinitrobenzene, right? Which is not what you want. If you did the same reaction on toluene, right, just treated this with nitric acid, 100% HNO3, and heated the crap out of it. Usually it takes heat to get the third one on. You would make 2,4,6 trinitrotoluene. Well-known explosive, TNT. So I feel like Walt would probably do this in his trailer. So that's a problem, right? The second nitro group isn't going where we want it. It's going in the other position. How can we solve that problem and get it to go where we want it on the adjacent position? So what we need to do is reduce that. Use radium nickel because that's the one we haven't used yet. To the NH2 group. So that has the advantage of changing the meta-director to an OP director. As well as taking a deactivated ring and converting it into an activated ring. So you got two things in your favor. Now what?
You have to protect the pair position.
Is that what you had in mind? SO3 gas, H2SO4 liquid, fuming sulfuric.
Oh, I think so. I didn't put it on the product, so I was confused. Wait, no.
Damn. Doesn't go where we want it. Why not? It is a great question. What's the first thing that's going to happen if we take amino benzene and treat it with concentrated sulfuric acid. The sulfur trioxide is going to watch while this base reacts with this acid to protonate the amine. And that's going to be a very favorable reaction because sulfuric acid is a strong acid. It reacts completely even with water, right? And the amine is a better base than water. The pKa of this guy, of the aniline, is around 5-ish. And that lone pair is actually even more reactive because you've got some electron donation coming in from this pi system, which is why this is a better acid. So that's a problem. And that's a problem because that no longer has a lone pair on the nitrogen to activate the ring or to direct it orthopara. It's now just an inductively deactivating group because of the positive charge on the nitrogen. So it's pulling that electron density away. You can't stop this acid-base reaction from happening because this has to be done in SO3 gas and concentrated sulfuric. The presence of water causes the equilibrium to lie towards the side that doesn't have the SO3 group on it. So we've got a problem. We have to stop this acid-base reaction from occurring. Otherwise, we can't get the NH2 group to act as the LP director. Go ahead.
The NH2 group is an OP director, so why the SO2 is adding on the end?
NH2 group is an OP director, but NH3 plus is not. NH3 plus is a meta director. The problem is the sulfuric acid reacts with the NH2 plus to form the NH3, or the NH2 lone pair to form NH3 plus, and that completely changes the character of the group that's attached. Right? In the absence of H2SO4, right, you might be able to get this to react with the ring, but you can't get this sulfonation reaction to go without having it in liquid H2SO4 because you need to prevent the SO3 from reacting with water. Right? SO3 is going to react more readily with water than it does with the benzene ring. So we've got to do something to this NH2 group to cause it to not do this. And then we can block it. So we need to protect this. And we protect it by converting it into an amide. Usually, if your amine is valuable, you'll put another base in there like triethylamine to react with the HCl. That's actually not strictly necessary because you could just use two equivalents of the aniline and use the aniline as the base to react with the HCl as well, but then you're wasting half of your starting material. So usually you put in either triethylamine or pyridine. Those are standard reagents that quench the base. Tertiary amines, right, they'll get protonated, but they won't do SN2 kind of reactions. So this is a nucleophilic acyl substitution, and you've seen this reaction before. Right? That's a pretty favorable reaction. This lone pair is no longer basic. So now I can actually react that with SO3 gas and H2SO4 liquid and put the protecting group, or put the blocking group on the para position.
So that is still an OP director?
It's still an OP director because it still has a lone pair on the nitrogen,
Okay.
but it's no longer basic. So the question is, why is it no longer basic? And the answer, as usual, is to look at the minor resonance contributor and notice that amides have a significant resonance form where they're donating to the carbonyl carbon. And that stabilizes that lone pair and makes it not want to react with acid. Right, so amines are basic, amides are not. And you know that this carbon-nitrogen double bond is enough of a contributor that it causes your carbon-nitrogen bond not to have free rotation. You saw that in the morpholine lab, where your enamine had free rotation, but your amide did not. So this group here instead of seeing two 4H triplets, what you saw was 6 hydrogens in one place and 4 in the other, because these CA2 groups are no longer magnetically equivalent. So this minor resonance structure is what causes there not to be free rotation about the carbon-nitrogen bond. It's what causes this carbon-oxygen double bond stretch in the IR to be at like 1680 instead of 1720 because it's weaker, because it's got significant single bond character. It's what causes the carbonyl group of the amide to be much less reactive than any of the other benzene derivatives because it's stabilized by donation from the lone pair. And it's what causes this to still be an OP director but no longer get protonated and converted into a meta director. So that's a really important resonance contribution. Now we can block it. Once it's blocked, this is now a meta director. And this is an OP director. So again, we've got both of the substituents agreeing that the place they want to put the next nitro group is in that ortho position. All right, so treat this with HNO3. H2SO4. And we can put that nitro group where we want it. We now have the two nitrogens attached to the ring in the right relative location. We can unblock using dilute sulfuric acid. All right, so step 1 was to nitrate it. Step 2 was to reduce it. Step 3 was to protect. Step 4 was to reversibly block the 4 position. Step 5 is to nitrate it again. Step 6 is to take that group off. All right, and we prevented this from happening. And all we have to do now is figure out how to convert that back into another NO2 group. So we have to deprotect the amide, convert that back to an amine, and then we have to oxidize amino group to NO2. So how do we do those two steps? Basically, what we're trying to do is hydrolyze that amide bond. This piece is irrelevant, right? If that were an NH2 group, we'd do the same thing to cleave that CN bond. So how do you hydrolyze an amide? Water would probably be a good choice. What else do we need in there? Base. So like KOH and water. Heat it up. Right, that will hydrolyze that bond. That's another nucleophilic acyl substitution. Just like this one, this is a nucleophilic acyl substitution. Right, so both putting it on and taking it back off are nucleophilic acyl substitutions. One doesn't have any water. The other one has water at base. And then how do we oxidize an NH2 group to an NO2 group on a ring? You just have to know it. Yep, CF3CO38. Peroxy acid. Peroxytrifluoroacetic acid will convert the NH2 group to an NO2 group. So we started with the NO2 group, but then we had to make it into an NH2 group to do everything else before converting it back to an NO2 group in the last step. So it's an 8-step synthesis. It seems like it would be a simple molecule, right? 1,2 dinitrobenzene. What could be easier than that? But it's not so easy to make because the NO2 group is a meta-director, and because the amine is basic enough that any strong acid in the presence of this amine is going to convert it into another meta-director, the NH3 plus group. Right? The NH3 plus group, the CF3 group, those are inductively electron withdrawing and deactivating because you have a positive charge or a partial positive charge next to the benzene ring. I think that's it. I think we're about 10:09. Yep. So there's more synthesis problems, obviously, in the textbook. There are some additional synthesis examples that I went over in the pre-recorded videos that you can look through. If you want to see me walk through a couple more. Should we have a synthesis quiz on Thursday? Practice? Let's have a synthesis quiz on Thursday. So you don't see it for the first time on the exam. Well, I mean, we could not have a synthesis quiz. We could have another reactions quiz. Let's have a synthesis quiz. You need practice. Otherwise, you're going to bomb it on the exam. You might bomb it on both, but hopefully not. And then on Thursday, we're going to talk about reactions of the aromatic compounds that are not electrophilic aromatic substitution. So nucleophilic aromatic substitution, the Chichi-Bobbin reaction, which is a fun reaction because Chichi-Bobbin is kind of a fun last name. Chichi-Bobbin reactions involves H- as a leaving group, so it's ridiculous. Absolutely ridiculous. Goddamn Russians.